Right now, without moving, without doing anything at all, you are being held. Something is pressing you into whatever surface you are lying on. You can feel it, the weight of your body, the gentle pressure of the mattress or the floor beneath you, the way gravity is pulling every cell in your body downward toward the center of the earth at 9.8 meters per second squared. You have felt this your entire life. You have never been without it for a single moment. And yet, you almost certainly have never thought about what it actually is. Gravity is the weakest force in the universe. A small fridge magnet can hold itself against the gravitational pull of the entire Earth. A child picking up a paperclip with a toy magnet is overpowering the gravity of a planet with a mass of 6 trillion kilograms. Gravity is so weak that every other fundamental force, electromagnetism, the strong nuclear force, the weak nuclear force, is stronger by factors that dwarf any number you have ever used. The electromagnetic force is 1,000 billion times stronger than gravity. The strong nuclear force, which holds atomic nuclei together, is even stronger than that. And yet gravity is the force that built everything. It pulled hydrogen atoms together into stars. It pulled stars together into galaxies. It shaped every structure in the observable universe across 13.8 billion years. The weakest force in existence made everything that exists. Tonight, we are going to follow gravity. From the apple falling in Newton's garden to the warping of space and time itself, from the force holding you to the ground right now, to the force holding galaxies together across billions of light years. This is the story of the most familiar thing in your life and the most mysterious. Somewhere in the telling of this story, you will drift. You will stop following the details and start feeling them. That is exactly what should happen. Because gravity is not just something to understand. It is something you are experiencing right now, in this exact moment, lying wherever you are lying, feeling the weight of your own body, feeling the planet beneath you, feeling yourself held by something that has been holding you since the moment you were born. The music enters now, deep and warm and slow, like something settling, like weight finding rest. And we begin the story where most people think it begins. In an orchard in Lincolnshire, England, in the autumn of 1666, with a young man sitting beneath an apple tree, watching something fall. But the story does not really begin there. The story begins earlier, in the spring of 1665, when the bubonic plague arrived in Cambridge. The university closed. Students and fellows scattered to the countryside, fleeing the disease that would kill a quarter of London's population in a single year. Among those who left was a 23-year-old student named Isaac Newton, not yet remarkable, not yet known for anything, returning to his mother's farm in Woolsthorpe, a small village 50 miles north of Cambridge, to wait out the plague in isolation. He stayed for 2 years, 2 years of enforced solitude, of empty days and no external structure, of a mind with nothing to do but think. And in those 2 years, Isaac Newton invented calculus, developed the theory of light and color, conceived the universal law of gravitation, and laid the groundwork for classical mechanics. He later called this period the most productive of his life. Most scientists produce nothing of comparable quality in an entire career. Newton did it in 2 years, alone on a farm, while the world outside was dying. The apple story is famous, so famous that it has been reduced to cartoon. Apple falls, Newton discovers gravity, end of story. But that is not what happened. Newton did not discover that things fall. Everyone knew things fell. What Newton discovered was much stranger and much more profound. He discovered that the apple falling from the tree and the moon orbiting the earth were the same phenomenon. That the force pulling the apple downward was the same force holding the moon in its orbit. That there was not one set of rules for earthly objects and another set of rules for celestial bodies. There was one force, universal, operating at every scale, describable by a single equation. The story, as Newton himself told it later in life, went like this. He was sitting in the garden at Woolsthorpe on an autumn afternoon when an apple fell from the tree above him. He watched it fall, straight down, perpendicular to the ground, and he began to wonder, why did it fall straight down? Why not sideways, or at an angle? It fell toward the center of the earth, always toward the center. No matter where you stood on the surface of the planet, objects fell toward the center. The force pulling the apple was directed toward the center of the Earth's mass.
And then he thought about the moon. The moon was not falling, or so it seemed. It stayed in the sky, night after night, moving in a great circular path around the Earth, never getting closer, never flying away. But why? What kept it there? The old answer, the one that had satisfied natural philosophers for centuries, was that celestial bodies moved in circles because circular motion was natural to them, because the heavens were perfect, and perfection expressed itself in circular motion. But Newton had already begun to doubt that. He had read Galileo. He knew that objects in motion stayed in motion unless acted upon by a force. The moon, moving in a circle, was constantly changing direction. Something had to be pulling it, constantly, toward the Earth, or it would fly off in a straight line into space. And then the leap. The impossible, extraordinary leap. What if the moon was falling? Not falling down to Earth, but falling around it. What if the moon was moving forward fast enough that the curve of its fall matched the curve of the Earth's surface, so that it was perpetually falling and perpetually missing? What if the moon and the apple were both falling, pulled by the same force, the only difference being that the moon was moving sideways fast enough to keep missing the ground? Newton sat with that thought. He did not publish it. He did not tell anyone. He worked on the mathematics, trying to prove it. And the mathematics worked. He could calculate the force required to hold the moon in its orbit, and it was the same force, scaled by distance and mass, that pulled the apple from the tree. One force, one equation. Every falling object, every orbiting moon, every planet circling the sun, all of it governed by a single relationship. He told it the law of universal gravitation. He called it the law of universal. Wow. Every object in the universe attracts every other object, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. The force of gravity between two objects equals the gravitational constant times the mass of the first object times the mass of the second object divided by the square of the distance between their centers. One equation. Every orbit in the solar system, every falling object, every ocean tide, predicted and described by a single mathematical relationship that a 23-year-old worked out during a plague. The implications were staggering. It meant that the same rules applied everywhere, on Earth and in the heavens, in the present and in the past and in the future. The universe was not a collection of separate realms with separate laws. It was one place, governed by principles that could be discovered by human reason and described by human mathematics. This was the birth of modern physics. Not the discovery of a single fact, but the discovery that the universe was knowable. Newton's equation was tested. It predicted the motions of the planets with extraordinary precision. It explained the orbits of comets. It explained the tides, the way the ocean rises and falls, in response to the gravitational pull of the moon and the sun. Edmund Halley used Newton's equations to predict that a comet he had observed in 1682 would return in 1758. Halley died in 1742, never seeing the comet again. But on Christmas night, 1758, exactly when Newton's mathematics said it would, the comet appeared. It has been called Halley's Comet ever since. In the 19th century, astronomers noticed something odd. Uranus, the seventh planet from the Sun, was not moving quite where Newton's equations said it should. Its orbit was wrong, off by a tiny amount, but measurable. There were two possible explanations. Either Newton's law of gravitation was incorrect, or there was an unknown planet beyond Uranus, pulling it off course with its gravity. Astronomers chose to trust Newton. They calculated where the unknown planet would have to be to produce the observed deviation in Uranus's orbit. They pointed their telescopes at that location. And on the night of September 23, 1846, Neptune was found, exactly where the mathematics said it would be. A planet discovered not by observation, but by calculation. By trusting that gravity was universal, and that the equations describing it were true. But for all his success, for all the precision of his predictions, Newton knew he had not explained what gravity actually was. He had described what it did. He had quantified it, measured it, predicted its effects with stunning accuracy. But he could not say what it was. How does the sun reach across 93 million miles of empty space and pull on the Earth? How does the Earth know the sun is there? What medium carries the force? What is doing the pulling?
Newton called this problem action at a distance, and it troubled him deeply. In a letter written late in his life, he said that the idea of one body acting on another across empty space without any mediating substance was so absurd that no one with a competent faculty of thinking could ever fall into it. And yet, his own equations required it. Gravity acted across distance, instantly, with no apparent mechanism. He could describe it. He could not explain it. The explanation would not come for another 230 years, and when it came, it would turn everything Newton had said upside down. The man who finally answered Newton's question was born in 1879 in the city of Ulm, in the kingdom of Württemberg, in what is now Germany. His name was Albert Einstein. And the answer he found was so strange, so far removed from everyday experience, that even now, more than a century after he published it, most people have never truly understood it. Not because they are not intelligent enough, but because the answer requires letting go of intuitions that feel absolutely certain. It requires accepting that space and time are not what they seem, that they are not fixed, not absolute, not the unchanging stage on which the universe performs. They are part of the performance. They bend, they stretch, they curve, and that curvature is what we call gravity. Einstein's path to general relativity, the theory that replaced Newton's gravity, began with a thought experiment. He imagined a man standing inside an elevator. The elevator is in deep space, far from any planet or star, floating in the void. The man feels weightless. There is no up or down, no sensation of gravity. Now imagine a rope is attached to the top of the elevator, and someone begins pulling it upward, accelerating it at 9.8 meters per second squared, exactly the acceleration due to gravity on Earth's surface. The man inside the elevator suddenly feels a force pressing him into the floor. It feels exactly like gravity. From inside the elevator, with no windows, no way to see outside, there is no experiment the man can do to tell whether he is standing still on the surface of a planet or accelerating upward in empty space. The two situations are indistinguishable. Einstein called this the equivalence principle, and he later said it was the happiest thought of his life. Acceleration and gravity are not just similar, they are equivalent. They produce the same effects. And if they are truly equivalent, then anything that happens in an accelerating reference frame must also happen in a gravitational field. This insight took 10 years to develop into a complete theory, 10 years of difficult mathematics, and false starts, and moments of despair. But when Einstein finally published the general theory of relativity in 1915, it was the most beautiful scientific theory anyone had ever produced. Here is what Einstein said: "Mass does not pull on other mass across the emptiness of space. Instead, mass warps the fabric of space and time around it." Imagine space as a stretched rubber sheet. Place a heavy ball in the center of the sheet. The sheet curves, dipping down around the ball. Now roll a smaller ball across the sheet. It does not move in a straight line. It curves toward the heavy ball, not because the heavy ball is pulling it, but because the sheet itself is curved, and the smaller ball is following the straightest possible path across that curved surface. The path looks curved to someone viewing the sheet from above, but from the perspective of the ball, it is moving in a perfectly straight line. The curvature is in the sheet, not in the ball's motion. This is what gravity is. Mass curves spacetime. Objects moving through that curved spacetime follow the curves. They are not being pulled. They are simply moving along the natural paths, the geodesics, through a curved geometry. What feels like the force of gravity is actually the shape of space. When you feel gravity pressing you into your bed right now, you are not feeling a force pulling you down. You are feeling the curvature of space-time created by the mass of the Earth. The Earth has bent the space around it. Your body, following the straightest possible path through that curved space, is moving toward the center of the planet. The ground is in the way, pushing up against you, preventing you from following that natural path. That pressure you feel, the weight of your body against the mattress, is not gravity itself. It is the ground stopping you from falling freely through curved space. The rubber sheet metaphor is helpful, but it is incomplete, because it only shows the curvature of space. Einstein's theory says that time is also curved by gravity. Time itself runs at different rates, depending on the strength of the gravitational field. The stronger the gravity, the slower time passes. At the surface of the Earth, time runs very slightly slower than it does in orbit. The difference is tiny, measured in billionths of a second per day, but it is real and measurable. GPS satellites orbit the Earth at an altitude of about 20,000 kilometers, where Earth's gravitational field is weaker than at the surface. Time on the satellites runs faster than time on the ground. The clocks on GPS satellites gain about 38 microseconds per day compared to clocks on Earth. That does not sound like much, but GPS works by measuring the time it takes for signals to travel from satellites to receivers. Light travels 30 centimeters in 1 nanosecond. 38 microseconds is 38,000 nanoseconds. If the satellite clocks were not corrected for relativistic time dilation, GPS would drift by more than 10 kilometers per day. Every time you use GPS to navigate, you are relying on Einstein's general relativity. You are relying on the fact that gravity curves time. Einstein's theory made predictions that were testable. One of the most famous was the bending of light. If space itself is curved by mass, then light, which travels through space, should follow that curvature. A beam of light passing close to the sun should be bent by the sun's gravitational field. Newton's theory also predicted a bending of light, because in Newtonian physics, light was thought to be made of particles, and particles have mass, so gravity should pull on them. But Einstein's theory predicted a bending that was exactly twice as large as Newton's. This was a clear, testable difference. If Einstein was right, starlight passing near the edge of the sun would be deflected by a specific amount. The problem was that stars are not visible near the sun under normal circumstances, because the sun is too bright. But during a total solar eclipse, when the moon blocks the sun's light, stars near the sun become visible. On May 29, 1919, there was a total solar eclipse, visible from the island of Principe, off the coast of West Africa, and from the town of Sobral in Brazil. Two teams of astronomers, led by Arthur Ebbington, traveled to these locations to photograph the stars near the sun during the eclipse. They measured the positions of those stars and compared them to the positions of the same stars photographed at night when the sun was nowhere near them. The stars near the sun during the eclipse appeared to be displaced from their usual positions. The light from those stars had been bent as it passed near the sun, and the amount of bending matched Einstein's prediction. It was twice what Newton would have expected. Space was curved. Light followed the curves. Einstein was right. The news made Einstein the most famous scientist in the world overnight. The headline in the Times of London on November 7, 1919, read, "Revolution in Science. New Theory of the Universe. Newtonian Ideas Overthrown." It was not an exaggeration. Newton had said gravity was a force. Einstein said, there is no force, there is only the shape of space. General relativity made other predictions, stranger and harder to test. One was the existence of gravitational waves. If space-time is a fabric that can be curved, then it can also ripple. When massive objects accelerate, particularly when they orbit each other or collide, they should send ripples through spacetime itself, like waves spreading across the surface of a pond. These gravitational waves would compress and stretch space as they passed, alternately squeezing and stretching everything in their path. The effect would be incredibly tiny. Even the most violent cosmic events, like the collision of black holes, would produce waves that, by the time they reached Earth, would distort space by less than the width of an atomic nucleus. For 100 years, gravitational waves remained a prediction without confirmation. The technology required to detect such a minuscule distortion did not exist. But, in the late 20th century, physicists began building detectors designed specifically to find gravitational waves. The most sensitive of these is LIGO, the Laser Interferometer Gravitational Wave Observatory, which consists of two identical facilities, one in Louisiana and one in Washington state. Each facility has two arms, each 4 kilometers long, arranged in an L shape. Lasers are bounced back and forth along the arms, and the interference pattern of the returning laser beams is measured with extraordinary precision. If a gravitational wave passes through the detector, it will compress space along one arm and stretch it along the other, changing the lengths of the arms by a tiny amount and shifting the interference pattern. On September 14, 2015, at 9:50 a.m. Universal Time, both LIGO detectors registered a signal. A gravitational wave had passed through the Earth. The wave compressed and stretched space by 1 part in 10 to the 21st power. To put that in perspective, it changed the length of LIGO's 4-kilometer arms by 1/10,000th the diameter of a proton. The signal lasted less than a quarter of a second. But in that signal, encoded in the frequency and amplitude of the wave, was the story of what had created it. 1.3 billion years ago, in a galaxy far from the Milky Way, two black holes, one 29 times the mass of the Sun and one 36 times the mass of the Sun, spiraled into each other and merged. In the final fraction of a second before they collided, they were orbiting each other at half the speed of light. When they merged, they converted 3 solar masses of matter into pure gravitational wave energy, rippling space-time itself. That ripple spread outward at the speed of light, crossing the universe for 1.3 billion years, stretching and compressing the fabric of space, until it passed through the Earth on a Monday morning in September. Moving the mirrors in 2 detectors in Louisiana and Washington by a distance 1/10,000th the width of a proton, and we measured it. We felt the universe ripple. Gravitational waves are now detected regularly. LIGO and its European counterpart Virgo have observed dozens of black hole mergers and neutron star collisions. Each detection is a confirmation of Einstein's theory. Each one is a direct observation of space-time itself, bending and flexing and carrying energy across the cosmos. Gravity is not a force. It is geometry. It is the curvature of the stage on which everything else happens. And now we can feel that curvature change. Einstein did not improve Newton's theory of gravity. He replaced it with something completely different. Newton said gravity was a force between objects. Einstein said there is no force. There is only the shape of space. When you feel gravity pressing you into your mattress right now, you are not feeling a force pulling you down. You are feeling the shape of the space created by the mass of the Earth. The Earth has curved the space around it. Your body, following the natural path through that curved space, is being guided toward the center of the planet. The ground is getting in the way. That pressure you feel, the weight of your body, is the ground stopping you from falling freely through curved space. If the ground were removed, you would fall, and in that fall, you would feel nothing at all. No force, no weight. Just the freedom of following the geometry. This is one of the most important ideas in all of physics, and it is worth sitting with for a moment. Gravity is not pulling you. Space is shaped around you, and you are moving through that shape. The universe is not a container with objects inside it. The universe is a dynamic, flexible fabric, and matter tells that fabric how to curve, and the curvature tells matter how to move. This is what the physicist John Archibald Wheeler meant when he said, "Matter tells spacetime how to curve, and spacetime tells matter how to move." It is a conversation, a feedback loop, playing out everywhere, at every scale, all the time. The Earth curves space. You move through that curvature. You also curve space by a tiny amount, and the Earth moves through your curvature also by a tiny amount. Every object in the universe is having this conversation with every other object, constantly, through the language of geometry. But understanding what gravity is, understanding the curvature of space-time, still leaves the question of what gravity does. And what gravity does, given enough time, is build everything. Without gravity, the universe would be a featureless void, a nearly uniform cloud of hydrogen and helium gas, expanding and cooling and never changing. Nothing would happen. No stars, no planets, no chemistry, no life, no structures of any kind. The universe would be perfectly boring. But gravity does not allow perfection. Gravity amplifies imperfection. It finds the tiny fluctuations, the regions that are just slightly denser than their surroundings, and it pulls on them, and in pulling on them, it makes them denser, which makes them pull harder, which makes them denser still. Given enough time, gravity turns the smallest imperfections into stars and galaxies, and everything in between. After the Big Bang, the universe was hot and dense and almost perfectly uniform. Almost, not quite. There were tiny variations in density, quantum fluctuations from the very earliest moments of the universe, stretched to cosmic scales by the rapid expansion called inflation. These fluctuations were tiny, less than 1 part in 100,000. But they were enough. In the regions that were slightly denser than average, gravity began to pull matter together. As matter fell into these regions, the density increased. As the density increased, the gravitational pull grew stronger. More matter fell in. A feedback loop, slow and patient and inexorable. For hundreds of millions of years, this process continued. The denser regions grew denser, pulling in hydrogen and helium gas from their surroundings, forming vast clouds that stretched across millions of light years. Within those clouds, smaller fluctuations formed, and gravity worked on those too, pulling the gas into tighter and tighter clumps. As the clumps grew denser, they grew hotter. When you compress a gas, its temperature rises. This is not unique to cosmic gas clouds. It happens in a bicycle pump. It happens in a diesel engine. Compression heats, and as these cosmic gas clouds compressed under their own gravity, their cores grew hot. In the very center of the densest clumps, the temperature climbed. 1,000 Kelvin, 10,000, 100,000, a million. 10 million. And at 10 million Kelvin, something extraordinary happened. The hydrogen nuclei in the core, which had been bouncing off each other for millions of years, were moving so fast that when they collided, they did not bounce. They fused. Two hydrogen nuclei combined to form helium, releasing energy in the process. The core of the collapsing cloud ignited. The first star was born. A star is a battle between two forces. Gravity is pulling inward, trying to collapse the star into the smallest possible volume. Nuclear fusion in the core is pushing outward, producing heat and pressure that resist the collapse. For most of a star's life, these two forces are balanced. Gravity compresses the core just enough to keep the temperature high enough to sustain fusion. Fusion produces just enough pressure to hold the star up against its own gravity. The balance is so precise that a star like the Sun can maintain it for 10 billion years. But the balance does not last forever. Eventually, a star exhausts its fuel. The details depend on the star's mass, but the outcome is the same. When the fuel runs out, fusion stops. The outward pressure disappears, and gravity, which has been waiting patiently for billions of years, wins. The core collapses. For a star like the Sun, the collapse stops when the core becomes dense enough that quantum mechanical pressure, the resistance of electrons to being squeezed into the same space, halts the collapse. The core becomes a white dwarf, a sphere about the size of the Earth, containing about half the mass of the Sun, slowly cooling over trillions of years. For more massive stars, the collapse is more violent. When a star more than 8 times the mass of the Sun exhausts its fuel, the core collapses in less than a second. The outer layers, no longer supported by the pressure from below, fall inward at a quarter of the speed of light. They hit the rebounding core and explode outward in a supernova, one of the brightest events in the universe, briefly outshining an entire galaxy. In that explosion, the star scatters everything it created during its life across hundreds of light years: carbon, oxygen, nitrogen, silicon, iron, calcium, phosphorus, all the elements heavier than helium, forged in the core of the star during millions of years of fusion, or created in the supernova explosion itself, are thrown into space, mixing with the surrounding gas clouds. Those enriched gas clouds are the raw material for the next generation of stars. Gravity pulls them together, just as it pulled together the first generation. But this time the collapsing cloud contains more than just hydrogen and helium. It contains the ashes of dead stars, and some of that material does not end up in the new star. Some of it forms a disk around the star, a flat rotating plane of gas and dust. Within that disk, gravity continues its work. Dust grains collide and stick together. Pebbles form, boulders, kilometer-sized planetesimals. The planetesimals collide and merge, growing larger, their gravity pulling in more material until they become planets. This is how the solar system formed. 4.6 billion years ago, a cloud of gas and dust, enriched by the deaths of earlier stars, began to collapse under its own gravity. Most of the mass fell into the center, forming the Sun. The remaining material formed a disk. Within that disk, rocky planets formed in the inner regions, where it was too hot for ice to condense. Gas giants formed farther out, where ice could form and provide enough solid material to build cores massive enough to gravitationally capture hydrogen and helium from the surrounding nebula. And gravity arranged it all, not with intention, not with design, but simply by following its own rules. The architecture of the solar system looks almost deliberate. Jupiter, the largest planet, sits at just the right distance to act as a gravitational shield, deflecting most comets and asteroids that would otherwise bombard the inner planets. Without Jupiter, Earth would have been hit by far more large impacts, possibly preventing the stable conditions necessary for complex life to evolve. The Moon, formed from the debris of a collision between the young Earth and a Mars-sized body called Gaia, stabilizes Earth's axial tilt. Without the Moon, Earth's axis would wobble chaotically over millions of years, causing wild swings in climate. With the Moon, the tilt stays nearly constant, giving Earth stable seasons over geological timescales. None of this was planned. It is simply what happened when gravity shaped the debris of dead stars into a planetary system. And it happened to produce a world where life could begin and persist for billions of years. Gravity's work did not stop at the scale of stars and planets. At the largest scales, gravity has shaped the structure of the entire universe. If you could step outside the universe and look at the distribution of galaxies, you would see something astonishing. Galaxies are not scattered randomly through space. They are arranged in an enormous web, a cosmic web of filaments, stretching across hundreds of millions of light-years, surrounding vast empty voids. Every galaxy is a node in this web. Every filament is a structure built by gravity. The web traces back to the same tiny density fluctuations that seeded the first stars. On the largest scales, those fluctuations created regions where matter was slightly more concentrated. Gravity pulled matter toward those regions, draining the voids and concentrating material along the filaments. Over billions of years, the red grew more pronounced. Galaxies formed at the intersections of filaments, where the concentration of matter was highest. The voids grew emptier. The filaments grew denser. Today, the cosmic web is the largest structure in the universe, a tracery of galaxies connecting across distances so vast that light takes hundreds of millions of years to cross them. And it all came from gravity, working patiently on quantum fluctuations smaller than an atom, amplifying them over 13.8 billion years into the scaffolding of the cosmos. Gravity is patient in a way nothing else is. Electromagnetic forces act in nanoseconds. Nuclear forces act in even tinier fractions of a second. But gravity works across billions of years, pulling, slowly and inexorably, on everything that has mass. It never stops. It never weakens entirely, no matter how far you go. Its influence extends to infinity, diminishing with distance but never reaching zero. Every object in the universe is gravitationally connected to every other object, however faintly. And given enough time, given billions of years, gravity builds stars and planets and galaxies and the conditions for life. Gravity is the architect of everything. The weakest force, the one that needed the most time, built the most. And gravity is still working. Right now, stars are forming in molecular clouds scattered throughout the Milky Way. Planets are coalescing around young stars. Galaxies are colliding and merging, their gravity pulling them together over hundreds of millions of years. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is moving toward us at about 110 kilometers per second. Pulled by the mutual gravitational attraction between the two galaxies. In about 4 billion years, Andromeda and the Milky Way will collide, their stars passing through each other like two swarms of bees, their central black holes eventually spiraling together and merging in a burst of gravitational waves. Gravity is bringing this about, slowly, inevitably, with no awareness and no intention. simply by being what it is. The story of gravity is the story of patience and scale, of tiny forces acting over enormous spans of time, of the weakest interaction building the largest structures. It is a story that spans from the quantum fluctuations of the early universe to the spiraling of galaxies, from the fall of an apple to the merger of black holes. And through all of it, gravity has been the constant, the patient architect, never resting, never stopping, pulling everything toward everything else, shaping the universe one atom at a time, across billions of years. But there is another side to gravity, a more extreme expression, a place where gravity is not weak at all, where it becomes so strong that nothing can resist it. This is the realm of black holes, where gravity wins completely. A black hole is what happens when gravity is given no opposition. When a very massive star, much more massive than the Sun, exhausts its nuclear fuel, the core collapses. But unlike smaller stars, where the collapse is eventually halted at its core of a very massive star, it contains everything from plastic. Its color is so heavy that nothing can stop it. The electrons are crushed into the protons, expanding no less possible. The neutrons themselves are compressed beyond the point where neutron degeneracy pressure can hold. The collapse continues. In less than a second, a core with a mass greater than the Sun is compressed to a point smaller than a city, then smaller than a mountain, then smaller than a house, smaller and smaller, the density rising without limit, until the entire mass is concentrated in a region of space so small and so dense that the escape velocity exceeds the speed of light. A black hole is born. The boundary around a black hole, the distance at which the escape velocity equals the speed of light, is called the event horizon. It is not a physical surface. You could pass through it without feeling anything unusual at the moment of crossing. But once you cross it, you cannot come back. Not because there is a force holding you in, but because all paths through spacetime, even the ones that point outward, curve back toward the center. Inside the event horizon, the future direction in time is the direction toward the singularity. Trying to escape a black hole once you have crossed the event horizon is not like trying to climb out of a deep pit. It is like trying to travel backward in time. The geometry of spacetime itself forbids it. Black holes are not holes. They are objects as real as stars or planets, but compressed to such an extreme density that they warp spacetime completely back on itself. The same force pressing you into your bed right now, the same force that holds the moon in orbit and pulls apples from trees, taken to its ultimate conclusion, creates a region of space from which not even light can escape. Gravity, the weakest force in the universe, becomes, in the form of a black hole, the most powerful. The singularity at the center of a black hole, where all the mass is concentrated, is a place where general relativity breaks down. The curvature of spacetime becomes infinite. The equations produce infinities, which in physics usually means the theory is being pushed beyond its domain of applicability. We do not know what happens at the singularity. General relativity cannot tell us. A complete theory would require a quantum theory of gravity, a way of describing spacetime at the smallest scales, and we do not yet have one. The singularity is hidden inside the event horizon, forever out of reach, forever unknowable to the outside universe. This is probably a good thing. Roger Penrose has proposed the cosmic censorship hypothesis. The idea that all singularities are hidden inside event horizons, that the universe does not allow naked singularities, singularities visible from the outside. It is a conjecture, not a proven theorem, but it seems to be true. Nature, it appears, has some modesty. Near a black hole, the effects of general relativity become extreme and undeniable. Time dilation, the slowing of time in a strong gravitational field, becomes pronounced. An astronaut falling toward a black hole would experience time normally from their own perspective. Their watch would tick at the usual rate. Their heart would beat normally, but an observer watching from a safe distance would see something very different. As the astronaut approached the event horizon, they would appear to slow down, moving more and more sluggishly, their clock ticking slower and slower. At the event horizon, from the perspective of the distant observer, time would stop. The astronaut would appear to freeze, hovering at the boundary, their image growing dimmer and redder as the light they emitted was stretched to longer and longer wavelengths by the intense gravitational field. The distant observer would never see the astronaut cross the event horizon, even though, from the astronaut's perspective, they crossed it and continued falling toward the singularity. This is not a trick or an illusion. It is a consequence of the way spacetime is curved near a black hole. Time is relative. Two observers in different gravitational fields, or moving at different speeds, will genuinely experience different amounts of time passing. There is no single universal clock. Time is local, personal, dependent on your motion and your position in spacetime. Near a black hole, this becomes impossible to ignore. At the center of our galaxy, the Milky Way, there is a supermassive black hole. It is called Sagittarius A. and it has a mass of about 4 million times the mass of the Sun. It is currently quiet, not actively consuming much material, but it is surrounded by a cluster of stars orbiting at extraordinary speeds. Astronomers have been tracking these stars for decades, watching them move in elliptical orbits around an invisible object at the galactic center. One of these stars, called S2, completes an orbit every 16 years. At its closest approach, it comes within about 17 light-hours of the black hole and reaches speeds of more than 5,000 kilometers per second, almost 2% of the speed of light. The orbit of S2 is a direct demonstration of a black hole's gravitational influence. The star is moving so fast in such a tight orbit that the only possible explanation is that it is orbiting an object millions of times more massive than the Sun, concentrated in a region smaller than the orbit of Mercury. Nothing but a black hole fits the observations. Almost every large galaxy has a supermassive black hole at its center, with a mass ranging from millions to billions of times the mass of the Sun. We do not fully understand how these black holes formed, or why they are so common, but they appear to play an important role in the evolution of galaxies. When a supermassive black hole actively consumes material, it becomes incredibly luminous, outshining the entire galaxy. The material falling toward the black hole forms an accretion disk, a swirling plane of gas, heated to millions of degrees by friction and compression. The accretion disk emits intense radiation, and some of the material is funneled along magnetic field lines and ejected in powerful jets that shoot outward at nearly the speed of light, extending for millions of light years. These jets can heat the surrounding gas, preventing it from cooling and collapsing to form new stars, regulating the growth of the galaxy. The black hole, a region of space from which nothing escapes, paradoxically becomes one of the most energetic objects in the universe. In April 2019, the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, released the first image of a black hole. The black hole was M87 star, at the center of the galaxy Messier 87, 55 million light-years away, with a mass of 6.5 billion times the mass of the Sun. The image showed a dark circle, the shadow of the event horizon, surrounded by a glowing ring of superheated gas. The image was blurry, limited by the resolution of the telescope, but it was real. It was a direct image of the boundary of a black hole, the edge of a region from which no light can escape, silhouetted against the glow of the accretion disk. The dark circle in the center was not the singularity. It was the shadow of the event horizon, the region of space where light is bent so strongly by gravity that it curves back on itself. The image was a confirmation of general relativity's predictions and a glimpse of gravity at its most extreme. Even black holes are not eternal. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon. The prediction is subtle and relies on the strange behavior of quantum fields in curved spacetime, but the result is that black holes slowly lose mass over time, radiating energy in the form of what is now called Hawking radiation. The temperature of this radiation is inversely proportional to the mass of the black hole. For a stellar mass black hole, the temperature is incredibly low, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole is actually absorbing more energy from the surrounding universe than it is emitting. It is growing, not shrinking. But in the far future, after the universe has expanded and cooled, and the cosmic microwave background has reshifted to near zero temperature, black holes will begin to evaporate. A stellar mass black hole would take 10 to the 60th years to evaporate completely. A supermassive black hole would take 10 to the 100th years. These are timescales so long that they are almost meaningless, longer than the current age of the universe by factors that dwarf comprehension. But they are finite. Given enough time, even black holes dissolve. Gravity builds and gravity destroys. It pulls hydrogen together into stars, and it crushes the cores of dead stars into black holes. It shapes galaxies and it tears them apart in collisions. It is creative and destructive, patient and inexorable, weak and overwhelming. It is the force that has been holding you since the moment you were born, and will hold you until the moment you die. It is the force holding the planet together beneath you right now, the force holding the moon in orbit, the force holding the sun in its path around the galactic center, the force holding the galaxy itself from flying apart into the void. And it is acting on you right now. You can feel it. The weight of your body against the surface you are lying on, that weight is not incidental. It is not background. It is gravity. It is the curvature of space-time produced by the mass of the Earth, guiding your body along the straightest possible path through that curved geometry, a path that leads toward the center of the planet. The ground is stopping you from following that path, and the sensation you feel, the gentle pressure against your back or your side or wherever you are resting, is the ground pushing up against you, resisting the geometry of space. The same force that built the first stars is holding you right now. The same force that shaped the cosmic web across billions of light years is pressing you gently into your bed. The same force that curves space-time around black holes is curving space-time around the Earth, and you are resting in that curvature. You are part of the gravitational web of the universe. You are not separate from it. You are held by it. You have always been held by it. The Earth's gravity is pulling you toward its center at 9.8 meters per second squared. That is the acceleration. If the ground were not there, you would fall at that rate, faster and faster, accelerating continuously until air resistance balanced the pull of gravity. But the ground is there. The ground is pushing up against you with exactly the force needed to keep you from falling. You are in equilibrium, balanced between the curvature of space-time pulling you down and the electromagnetic forces in the atoms of the ground pushing you up. The force you feel is the result of that balance. But you are not just feeling gravity. You are also exerting it. Every object with mass curves space-time. Every object with mass exerts a gravitational pull on every other object. You are exerting a gravitational pull on the Earth. It is tiny, negligible, compared to the Earth's pull on you, but it is real. You are also exerting a gravitational pull on the Moon, on the Sun, on every planet in the solar system, on every star in the Milky Way, on every galaxy in the observable universe. The force is unimaginably small, diminishing with the square of the distance, but it is not zero. It is real. At this exact moment, you are gravitationally connected to everything in the universe. The Moon is pulling on you, too. The Moon's gravity is strong enough to raise the oceans by meters twice a day, creating the tides. It also raises the solid rock of the Earth's crust by about 30 centimeters. The tidal force is the difference in gravitational pull between the near side and the far side of an object. The side of the Earth facing the Moon is pulled slightly more strongly than the center of the Earth, and the center is pulled more strongly than the far side. This differential force stretches the Earth slightly along the Earth-Moon line. Your body, which is largely water, is also subject to tidal forces from the Moon. The Moon is pulling on the water in your body right now, slightly more strongly on the side facing the Moon, slightly less on the other side. The difference is immeasurably small, but it is real. The Moon is tugging on you, gently, right now, as you lie in the dark. Gravity is the most intimate force. It is always present. It is always acting on you. You cannot turn it off. You cannot shield yourself from it. Every moment of your life, from your first breath to your last, you are held, and wherein the Moon shines from, a fate part. It is the first time you felt. It is the thing that makes you feel heavy when you are tired, the thing that makes lying down feel like relief. It is what makes a bed comfortable, what makes a pillow restful. The sensation of being supported, of being held, is the sensation of something resisting gravity on your behalf. The mattress is holding you up against the pull of the Earth. and in doing so, it allows you to rest. In orbit, astronauts experience weightlessness. They are not beyond the reach of Earth's gravity. They are still well within it. The International Space Station orbits at an altitude of about 400 kilometers, where Earth's gravitational pull is only about 10% weaker than at the surface. The astronauts feel weightless, not because there is no gravity, but because they are in free fall. They are falling toward the Earth continuously, and the Earth is curving away beneath them at the same rate, so they never get closer. They are falling and missing, just like the moon, just as Newton realized 3.5 centuries ago. In freefall, there is no sensation of weight. The body does not press against anything. There is no up or down. Astronauts describe it as the most peaceful physical sensation they have ever experienced, a complete absence of the feeling of weight that they have carried their entire lives. The sensation of weight is not gravity itself. It is the resistance to gravity. It is the ground, or the chair, or the bed, pushing up against you, preventing you from falling freely through the curved spacetime around the Earth. If the ground were suddenly removed, you would fall, and in the first moments of that fall, before air resistance became significant, you would feel weightless. You would be in free fall, following the natural geodesic through space-time, and there would be no force acting on you at all. This is what Einstein meant by the equivalence principle. Free fall and weightlessness are the same thing. Gravity is not a force you feel. It is a curvature you follow. The force you feel is the resistance to that curvature. Right now, lying still, you are being held by the Earth. The mass of the Earth, 6 trillion kilograms, is curving the space-time around it, and you are resting in that curvature. The ground is supporting you, resisting the natural path you would follow through curved space, and that resistance is what you feel is weight. It is not a burden. It is not something to overcome. It is simply the shape of space, and your place in it. The feeling of gravity is the feeling of being connected to the planet, of being part of something vastly larger than yourself. The Earth is holding you, and it has been holding you every moment of your life. Even when you jump, you are not escaping gravity. You are briefly in free fall, following a parabolic arc through curved space-time, and then gravity guides you back to the ground. You cannot leave. Not without extraordinary effort, not without rockets and speeds of 11 kilometers per second, the escape velocity of Earth. And even then, you are not leaving gravity. You are only leaving Earth's gravity. The sun's gravity takes over. The galaxy's gravity. Gravity extends infinitely. There is nowhere in the universe that is free from gravity. Everywhere, space is curved by mass. Everywhere, objects follow the curves. Gravity is universal. There is something deeply comforting in this. You are not adrift. You are not floating in an indifferent void. You are held. The planet is holding you, has been holding you since birth, will hold you until you die. And the planet itself is held by the sun, and the sun is held in its orbit around the galactic center, and the galaxy is held in the cosmic web, and all of it, every bit of it, is connected and by the curvature of space-time, by the universal attraction of mass for mass. You are part of that web. You are a node in it, tiny but real. The universe is holding you. And right now, as you lie in the dark, feeling the weight of your own body, feeling the pressure of the mattress beneath you, you are feeling that connection. You are feeling the curvature of space-time. You are feeling the shape of the universe around you, the way the mass of the Earth has bent space, and the way your body, moving through that bent space, is being guided gently downward, toward the center, and the way the ground is resisting, holding you up, keeping you suspended between falling and resting. This is what gravity is, not an abstract equation, not a theoretical curvature, but the feeling you have right now, the weight of your head on the pillow, the pressure of the mattress against your back, the gentle, constant pull toward the center of the Earth, the sensation of being held. Gravity is the weakest force in the universe. A tiny magnet can overcome the gravity of an entire planet. The electromagnetic forces holding the atoms of your body together are incomparably stronger than the gravitational attraction between those atoms. And yet gravity is the force that built everything. It is the force that pulled the first stars together from the primordial hydrogen cloud, the force that shaped galaxies, that formed planets, that created the conditions for life. It is the force holding you right now, and the only thing that comes from the atoms.
The force you feel in your body every moment, the most familiar and the most mysterious. Tonight, you have followed gravity from Newton's garden to the curvature of spacetime, from the apple falling to black holes and gravitational waves, from the cosmic web to the feeling of your own weight against the bed. Gravity is all of these things. It is an equation and a sensation, a curvature and a force, the architect of the universe, and the pressure you feel when you lie down.
And now, lying in the dark, you can feel it. The Earth is holding you. It has curved the space-time around it, and you are resting in that curvature. The ground is beneath you, solid and patient, pushing up against you with exactly the force needed to keep you from falling. You are suspended. You are held. You are part of the gravitational web of the universe, connected to every star and every galaxy, however faintly. The same force that built the stars is pressing you gently into your bed. The same force that will, billions of years from now, pull the Milky Way and Andromeda together in a slow galactic collision. The same force that holds the moon in its orbit, that raises the tides, that keeps the planets circling the sun. All of it is present in this moment, in the weight of your body, in the feeling of being held. Gravity is pulling you toward the center of the Earth at 9.8 meters per second squared. The ground is holding you up. You are perfectly suspended between falling and resting. The same force that built the stars is the force making you feel heavy right now. Feel it, the weight of your body against the surface beneath you. That is the universe holding you. It has held you your entire life. It will hold you as you drift now, as your thoughts slow and your breathing deepens, and the details of Newton's equations and Einstein's curvature fade into the background. The science becomes sensation. The understanding becomes feeling. You are held. You have always been held. Gravity has never, for a single moment of your existence, let you go. Rest now. The planet is beneath you. The ground is solid. Space is curved around you in a shape that's been holding you since birth. You do not need to hold yourself up. The ground is doing that. The Earth is doing that. Gravity, the weakest force in the universe, the force that made everything, is doing that. You are part of the structure it built. The pattern of atoms arranged by chemistry that was made possible by stars that were made possible by gravity. The carbon in your body was forged in the core of a star that died billions of years ago. The oxygen you are breathing was made in a supernova. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it was made in stars, scattered by stellar explosions, gathered by gravity into new clouds, collapsed into new stars, formed into planets, and eventually assembled into you. You are made of stardust, held together by forces stronger than gravity, but resting now in gravity's gentle, constant pull. The weight you feel is not a burden. It is a connection to the ground, to the planet, to the history of the universe. Every atom in your body has been on a 13.8 billion year journey from the Big Bang to this moment. And right now, that journey has led you here, to this bed, this room, this night, held by the same force that has been shaping the universe since the beginning. There is nothing you need to do. Gravity is doing the work. It is pulling you down. Where was the time to the future? Where was the wool?
The ground is pushing you up. You are balanced between the two, perfectly supported, perfectly held. The curvature of spacetime around the Earth is guiding you, and the electromagnetic forces in the atoms of the mattress are resisting that guidance. And the result is this sensation, this feeling of weight, of rest, of being supported.
Let yourself feel it. The pressure against your back, your shoulders, your legs, the way the mattress conforms to the shape of your body, the way your body settles into it. This is gravity and resistance in equilibrium. This is the shape of space-time made tangible. This is the universe holding you. Your body knows this feeling. It has felt it every day of your life. When you were born, you felt the weight of your own body for the first time, and you have been feeling it ever since. It is the most constant sensation you have, more constant than sight, than sound, than any other sense. Gravity is always there, always pulling, always present. And right now, as you rest, it is doing what it has always done, holding you, gently, inexorably, without pause. Astronauts who return from months in orbit, months of weightlessness, say that the first thing they notice when they come back to Earth is how heavy everything feels. Their arms, their legs, their head, everything weighs so much. And at first, it is uncomfortable, but then it becomes comforting, because it is familiar, because it is home, because weight is the sensation of being held by the planet, and after months of floating, that sensation is a relief. You do not need to go to orbit to feel that relief. You are feeling it now. The weight of your body is the Earth holding you. The mattress beneath you is resisting on your behalf, and the result is rest. Perfect, stable, supported rest. The moon is above you somewhere, pulling on the oceans, pulling on the land, pulling on you. The sun is somewhere beyond the horizon, holding the Earth in its orbit, holding the entire solar system together. The galaxy is rotating slowly around its center, where a black hole 4 million times the mass of the sun curves space-time into a knot. And all of it All of it is connected by gravity, by the curvature of space, by the gentle, patient pull of mass on mass across the vast distances of the universe. And you are part of it, lying here in the dark, feeling the weight of your own body. You are part of the cosmic web. You are held by the earth, which is held by the sun, which is held by the galaxy, which is held in the vast structure of the universe. Every part connected to every other part. Every mass pulling on every other mass. And in this moment, the force holding you is the same force holding galaxies together across billions of light years. Gravity is not separate from you. It is acting on you, through you, because of you. You have mass, and mass curves space-time, and the curvature you create is part of the total curvature of the universe. You are not a passive object in a gravitational field. You are part of the field. Your presence changes it, however slightly. The earth is falling toward you, just as you are falling toward the earth. The difference in acceleration is immeasurably small, but it is real. You matter, literally. You are made of matter, and matter gravitates, and the universe is shaped by the sum of all gravitational interactions, including yours. This is not metaphor, it is geometry. And this is not metaphor, it is geometry. The space-time around you is slightly curved by your presence, and every object in the universe, from the moon to the most distant galaxy, is following a path through space-time that is infinitesimally different because you exist. But right now, the only curvature you need to think about is the curvature created by the Earth. The gentle, constant curvature that is guiding you downward toward the center of the planet, and the ground that is stopping you, holding you, allowing you to rest. Feel the weight of your body, not as a burden, not as something heavy, but as a connection, as the shape of space made tangible, as the universe saying, you are here, you are real, you are held. The force pulling you down is the same force that pulled hydrogen into the first stars, the same force that built the galaxies, the same force that will, in the unimaginably distant future, shape the final structures of a cooling, expanding universe. It is the weakest force, and it is the most patient, and it is the one that built everything. And right now, it is holding you, pressing you gently into the surface beneath you, reminding you that you are not floating, you are not adrift. You are anchored to a planet, held by a force that has never failed, that has never wavered, that has been pulling on you every moment since you were born. Rest into it. Let the weight of your body settle. Let your muscles relax. You do not need to hold yourself up. Gravity and the ground are doing that. You do not need to resist. There is nothing to resist. You are exactly where you are supposed to be, held in the curvature of space-time, suspended between the pull of the earth and the support of the surface beneath you. This is rest, not the absence of force, but the balance of forces. Gravity pulling, the ground resisting, your body suspended between them, perfectly balanced, perfectly still, perfectly held. The universe is vast, 13.8 billion years old, 93 billion light years across, filled with 2 trillion galaxies, each containing hundreds of billions of stars, and all of it is connected by gravity, shaped by gravity, held together by the curvature of spacetime. The cosmic web stretches across the observable universe, a structure so large that light takes hundreds of millions of years to cross it, and at the center of that incomprehensible vastness, at the center of all that scale, is this moment, you, lying in the dark, feeling the weight of your own body, held by the earth. The stars were built by gravity. The planets were built by gravity. The conditions for life were created by gravity. And now gravity is holding you as you rest, as your breathing slows, as your thoughts drift, as the distance between waking and sleeping narrows to nothing. You are safe. The ground is beneath you. The earth is holding you. The same force that shaped the universe is pressing you gently into your bed. There is nothing to fear, nothing to worry about. You are held. You have always been held, and you will be held as you drift now into sleep. As the science fades and the sensation remains, as the weight of your body becomes the only thing you feel, and then, slowly, even that fades, and there is only rest, only the deep, quiet comfort of being held by the planet, by gravity, by the shape of space itself. Rest now. The universe is holding you. It has held you your entire life. It will hold you through the night. There is nothing you need to do. Gravity is patient. Gravity is constant. Gravity is here. And so are you, held in its gentle, inexorable pull, safe, supported, at rest. The weakest force in the universe made everything that exists. And right now, it is making you feel heavy, making you feel held, making you feel safe. Let it. Let gravity do what it has always done. Let the earth hold you. Let the ground support you. Let your body settle into the curvature of space-time that has been waiting for you since the universe began. You are exactly where you belong, held by the planet, part of the cosmic web, connected to everything, at rest. Sleep now.